All right, so we're going to continue 7.5, exploring a general strategy for integration and actually doing the integrations, okay? So we'll start with we're just going to do some examples, and we're going to show how we're applying that critical thinking to find the right technique for solving these, okay? And in fact, I'm even going to show you that it's possible that you're going to go one way and it may not be the lead that you want, okay? All right, so let's start with this example. We're going to evaluate sine cubed x over cosine x. Find the integral of that function. Okay, so where do we begin? Why don't we start with, let's write this as, let's see, what would work? Sine squared of x over cosine of x times sine of x. Let me tell you why I'm thinking we should do this. So sine squared, I can write it in terms of cosine squared. And then if I split off a sine, then that'll give me the opportunity to do a u substitution in a little bit. All right, so let's start with that. So we know that I can write it that way. And I'm going to go 1 minus cosine squared x over cosine x times sine of x dx. And then that should be some rational function in terms of u if I let u be cosine of x. Okay, so good so far. Let's go ahead and just write that in. Okay, it's going to be 1 minus cosine squared of x over cosine of x times sine of x dx. I'm going to let u be cosine of x, which lets du be negative sine of x dx. Then it's going to be negative integral 1 minus u squared over u times du. I already pulled out a negative so that we don't have to worry about that right now. We'll just have du there. And this, if I split up, so the numerator has a higher degree than the denominator, and I'm just going to split up the numerator into 1 over u du, so du over u, plus the integral of u squared over u, which is u du. Okay, not bad. Then I have negative ln of u plus u squared over 2, not du, we're done with that, plus c. And u was just cosine of x all along, so we have equals negative natural log cosine of x absolute valued plus cosine squared x over 2 plus c. Done. Nice. Okay. So in this case, let's see. Let's break down what we did. So first we simplified. We used a trig identity. And we knew to do that because we wanted to exploit a substitution. And once we had that, then we can use, an assortment of other basic rules. So this is very similar to the more general techniques that we discussed in the trig integrals. But the key insight here was to think about how to simplify first. And so even if you forget how to use those techniques that we learned in 7.2, we can rediscover them by applying this more general strategy. So it really is quite powerful. Okay, new example. I'm going to evaluate the integral of e to the square root of x dx. Okay, e to the square root of x dx, it's so frustrating. It looks like it should be something that we can handle, okay? But I don't know. If it'll make it easier, why don't we go ahead and replace this then using u substitution. So we're going to let u equals square root of x, which means equivalently x equals u squared. Now this really only works for x being positive, okay? We're going to ignore that for now, but just be aware that that is an issue here, okay? So if x equals a u squared, then dx equals 2u du, and that's going to be helpful when we replace this back in, because now we're going to have e to the u, and dx is 2u du. So this isn't that great, but it is at least a step forward from what we did, from where we started. It's at this point that you should recognize that we can use integration by parts, because we have the product of two functions, one of which we're going to divide, and one of them that we're going to integrate. So we're going to here we're going to need to use different letters. Don't get too confused here, okay? All that matters when doing integration by parts, it's not the letters we chose. It's that we chose two letters, and we're going to use, well, I'll get to it in a second, but we're going to let v equal u, which means dv equals du. dw is e to the u du, which means w is e to the u, okay? And in this situation, so we have integral of v dw. We're going to replace that with vw minus the integral of w dv. Okay, so we're just shifting the letters a little bit. Don't lose your cool. So we have 2 times vw u e to the u minus the integral of w dv, e to the u du. Not bad, right? So it's going to give us 2 u e to the u minus e to the u plus c. So, and we can factor out a u and e to the u, that's fine. We're going to get 2 e to the u, u minus 1, plus c, or plus 2c, I should say, sorry. That's why I should have left it until the very end, but I'm going to replace that with a different c at some point. Right, and then we just replace u back, because we have to, in terms of the original variable being x, so we have 2 e to the square root of x times u minus 1, so u is square root of x, minus 1, plus 2c, which I'm not going to call c1. That's your answer. It's not bad. Okay, so let's recap. What strategies did we use here, okay? So we performed a substitution. That was advantageous, because we literally could not handle this at first, right? There was nothing we could do except perform the substitution. Once we had the substitution, we identified that quickly we could use integration by parts. And then just followed our noses, carried through the integration by parts, resubstituted, and there you go. Not bad, okay? So this illustrates when, you may need it, you may have a hidden integration by parts, okay? All right, here we go. Let's do another example. So we want to evaluate the integral from 0 to 1 of x square root of 2 minus square root of 1 minus x squared dx. Okay. Whew. So how can we do this properly? Well, first things first, let's identify all the pieces, because there's a lot going on here, right? So I am noticing this right here, which suggests that we may be able to use a trigonometric substitution. Namely, if we let x be sine of theta, then dx will be cosine of theta d theta which gives us square root of 1 minus x squared, will be cosine of theta. And we'll transform the limits. So theta of 0 is going to be sine inverse of 0, which is 0. And theta of 1 is sine inverse of 1, which is pi over 2. Okay. So those are all the pieces of the substitution that we need so far. So we have equals the integral from 0 to pi over 2 of x, which is sine of theta, times the square root of 2 minus cosine of theta, because the square root inside the square root turns into cosine, times cosine of theta d theta. Okay. Wow, that's weird, right? What do we do with this? Well, don't freak out. We have two cosines and one sine. What if we perform a substitution with cosine involving sine? So I'm going to switch the order of the cosine and the sine. So cosine of theta times square root of 2 minus cosine theta times sine of theta d theta, which suggests yet another substitution, which is basically I'm going to let u be cosine of theta, du is going to be negative sine of theta d theta. And, well, let's transform the limits again. So u of 0, cosine of 0 is 1. U of pi over 2 is root 2 over 2. Okay. Good so far? Not bad, right? Okay. Wait, is that right? No, sorry. Pi over 2. No. Negative 1. No, again, that's also wrong. Cosine of pi over 2 is 0. Okay, there we go. This means it's going to be the integral from 1 to 0 of u times the square root of 2 minus u times du. Negative. I'm gonna take care of the negative actually by switching the order of integration. Okay, let's do that first. So this is going to be integral from 0 to 1, interesting, of u square root of 2 minus u du. That's allowed, right? That's a basic property of integrals. Okay, now what do we do? Don't worry, we got this. It's not bad. Remember, this is another product, right? So we have u and square root of 2 minus u. Which one do you think would be easier to integrate or derive? If we derive u, then we'll get a dv that's equal to du. Let's go with that. So we're going to let v equal u, dv equals du. dw is now going to be 2 minus u to the 1/2 power du. Okay. And if we integrate this, we get w equals negative 2/3 2 minus u to the 3/2. Okay, now we can apply the integration by parts. So it's going to be equals vw, which is u times negative. I'm going to go ahead and just stack them. Well, let's go ahead and multiply them together directly. 2 minus u 3/2 minus the integral of negative 2/3 2 minus u 3/2 du from 0 to 1. Then this is negative 2/3 u 2 minus u to the 3/2 plus 2/3 times 2/5 of 2 minus u to the 5/2, all from evaluated from 0 to 1. All right, now we can just plug in, basically. So I'm going to have, if I plug in 1, right, so I get negative 2/3. 2 minus 1, which is 1, to the 3 halves, plus 4/15 times 2 minus 1 to the 5 halves, so that's just 1. And then minus, plug in 0 gives you nothing for the first term. And then for the second term, that's going to give you 4/15 times 2 to the 5 halves. All right, almost there. We're almost there. Okay, then let's see, am I following everything correctly? We're doing good so far. Remember, at this point, we don't have to substitute anything back because we've already transformed the limits and we're already almost done. So 4/15 minus 2/3, that's going to give us negative 14/15. Is that right? No, because if it's negative 2/3 plus 4/15. Let's try this again. Multiply by 5 to negative 10/15 plus 4/15 minus 4/15 times 2 squared times root 2. And I know that because 5 halves becomes 2 1/2. So there's 2 whole powers of 2 and a 1 fractional half power of 2. All right, we're almost there. Negative 6/15 minus 4/15 times 4 root 2, which gives negative 2/5 minus 16/15 root 2. And that's our answer for this one. Okay, let's go back and check. Let's see what strategies we needed to use, right? So we needed to perform a sign substitution, right? We identified that using our knowledge of what we needed to tackle here. Okay, then we did some clever simplifying. Simplifying can also mean rearranging. That's totally part of the process here. Then we performed another substitution. And in this substitution, then we were able to get, now we needed to perform integration by parts. Okay. Lastly, just following a bunch of algebra here. Following our nose with this one. It's not super nice, but it's part of it. Okay, another example. Let's evaluate the integral of e to the 2x over 1 plus e to the x dx. Okay, this one it's giving a similar flavor to what we did in a previous problem. So in the very last video that we saw in the last section, we saw that when we can rationalize sometimes the integrands using a clever substitution where we replace basically the non-rational part. Here I'm going to write this as e to the x over 1 plus e to the x times e to the x dx. And the hope there is that if we use u equal e to the x, then we know du is e to the x dx. And so this whole thing becomes u over 1 plus u times du. Okay, now that's rational, okay? But how do we tackle this, right? We can't perform a substitution yet. There's nothing that we can do with partial fraction decomposition. But notice, this is important, since the degree of p equals the degree of q, we perform long division. So in this case, we're going to divide u by u plus 1, which seems like, what would that even do? Basically, it does this. So write it as u plus 0. So you're dividing u plus 0 by u plus 1. That's going to give us, we're going to need to multiply by 1 to give us u plus 1. And the remainder then is going to be negative 1 minus 1 over u plus 1. And that we can handle because the integral becomes 1 minus 1 over u plus 1 du. So this is the integral of du minus the integral of du over u plus 1. That is an application of natural log. So we get u minus natural log of absolute value of u plus 1 plus c. And then we can replace back our u, which was e to the x. So equals e to the x minus natural log of e to the x plus 1 absolute value bar plus c. Not terrible. Okay. And now let's revisit what's going on, what went on in this problem, right? So in this problem, we split off an e to the x. So we're simplifying in the form of, it's not really simplifying in the sense that we're writing it in a simpler form, but we're rearranging and performing some algebra here to make it not work for us by applying a substitution. Then we did long division to get a simpler rational function. And now we're using our rational function techniques. In this case, it was as simple as splitting it into two rationals, one just being just 1, and the other one being 1 over u plus 1, for which we can apply a natural logarithm. And that's about it. So there are all sorts of exciting, exotic examples to tackle here, but this encapsulates most, or a very, very large majority of the